Hello everyone, welcome back to the generative AI course. So today specifically we are going to talk about this fundamental of transformers and architecture. There we are going to cover the encoders, decoders and BERT and the GPT model. So in AI basic we understood that how artificial intelligence has evolved significantly from 1950s to current era, where we started with a rule based and then we moved to machine learning and now we are into generative AI. So machine learning actually deals with the pattern recognition, decision making, and while the DL uses neural network for complex tasks like image processing, speech recognition, and automation across industries. So today we'll continue the discussion and we'll talk about the fundamental concepts of transformers, NLP, and talk about the architectures and components. So we'll start with the natural language processing. This NLP is a part of artificial intelligence and that teaches computer to understand, interpret, and generate human language. So in simple terms, what it does is it allows a machine to read text, hear speech, and then figure out what you mean, what you feel, and what are you asking. So in day-to-day life, we see example of this Siri and Alexa, which understand the natural language, whatever we are trying to put a speech over there, and then process that speech and reply us or do any task based on that. So why we require NLP? So NLP actually bridges the gap between the human and computers. Everyone need not to be very proficient into giving commands to computer. Now in today's era, anyone who understand the natural language, who speaks the language English, can actually talk to any computer and give the commands to do the any processing. So that where the NLP comes into picture, is bridging the gap between humans and machine. So we'll a bit talk about the old NLP world, what it used to be like. So earlier models, is because we are directly going to the models because we are focused on transformers, the new era transformers today. So we'll be talking about a bit of old stuff which is redundant now, which is obsolete now. But just to get a flavor of how it used to be earlier, we'll talk about this RNN and CNN. So before the era of transformer, the world of NLP looked very different. So machine used to struggle to understand the context of human language and often getting bogged down by the long sentences and the complex formation of the sentence. And why? Because of that, because earlier the traditional model used to process the information word by word, the sequentially. So this RNN and CNN, which you are seeing over here, are the traditional NLP models which process every sentence by reading it loud. So you can assume that for any sentence, I want to visit to bank. So it will understand, it will read the sentence word by word, but it will not get the context. If I give a long sentence to it, and if the context is provided in the far back sentence, for example, I am going to bank because I need to deposit the cash. RNN, what it does is because it read word by word and based on the memory, it keeps everything into the memory. And if it loses the context that I'm going to bank and I need to deposit the dash, then it will not able to give me the right answer because the sentence I'm going to bank is forgotten by this model because it's basically predicting the word which is based on the previous word. So that's why it struggled. If I say struggle to understand the nonsense of the human language and often bogged down by long sentences, as we talked about already. So in the RNN, which is recurrent neural network, so as I said, sequential processing happens and model often forget the early part. And though it's with the LSTMs, that is long short term memories, it is being managed a bit, but that also not solving the fundamental problem of remaining or keeping the context entirely of the entire long sentence. Then came a revolutionary idea inspired by humans pay attention, that is self-attention. So we have this concept of self-attention where imagine reading a sentence. As you read each word, your brain doesn't focus on the previous word. It quickly consider how every other word in the sentence might influence its meaning. The same example I gave you, I am going to bank because I need to deposit the cash, or I am going to bank because I need to catch the fish. If I say catch the fish, that means I meant to say that I am going to a river bank, not the actual this bank which contains the cash or it's not related to money. So each word in a sentence, self-attention calculates its relevance to every other word. So it does by creating three internal ideas, that is query, key, and value. So based on this query, key, and value, it actually checks the weightage of that word. So in example, we are given this: the quick brown fox jumps over the lazy dog. So over here, query is one of the word that is compared to the key of other word, giving an attention score. So how important that are to each other. So the scores then tells the model how much weight or consideration it should be given to that word. So it's creating a rich context aware understanding for each word. So that's a concept of self-attention. And this self-attention became the very groundbreaking concept or became very groundbreaking architecture in all the modern transformers. So the transform model completely stopped processing words one by one now. Like the RNN model, the older models are not in place. Like those are obsolete now. So what it does, like it processes the entire chunk of information at the same time and in a much faster way. So right now, like all the transformers, we'll talk about them like later on also. So the transformers normal architecture is that we have an encoder block and we have a decoder block. So just give it a glance to this image. We have this encoder block and this decoder block. So the input is given as a quick brown fox, and what it does is it breaks that entire sentence into the tokens, into the words, and then it creates an embedding. So we'll talk about this embedding concept also like in detail. So embedding is actually like giving a numerical denotation to the words so that it can be passed on to the subsequent processing algorithms. And then we have this multi-head self-attention, which is very much critical component of this encoder. So this is basically core. It checks how important every single word in the sentence is to every other word. The multi-head is why we say is multi-head, because it does the same processing multiple times and focusing on different things, grammar, tense, meaning each time. And once it's done with the processing, then it passes that to the feed forward network. So what this feed forward network is, you can consider that as a fact checker, which checks, okay, after the attention layer, this attention layer process this input, and this layers process each word data individually. It runs a quick check and refine process on the new and context switch numbers, because it's happening multiple times. So every time if context change, then it again checks that concept, okay, whether we are getting a polished version or not. So that's the core responsibility of this feed forward network. And then we do a bit of this normalization where the data cleaning up happens. And once we have this input or the brief summary ready for our decoder, so over here, then it gets passed to the decoder. So decoder job is to take the encoder summary and generate the output sentence. So example, over here, if you want to translate this into French, then the summary of this input will be transferred to decoder so that it can translate that, or it can put output that is into French translation. You will see, like, again, here is a core component that is masked multi-head self-attention. So over here we have this masked, and over here this multi-head self-attention. What does this mask mean is similar to the encoder's attention, but with a mask. It only lets the model to look at the word it has already generated. So it will not allow the model to generate a new response, but just to again check the history of the generated words. And again, we have this feed forward network, which again check for the polished version, the final version. And the layer refines the word's numerical representation after it has received all the contextual information. And then we have this softmax, that is the actual final step, where linear layer converts the processed numbers and a huge list of probable words, and softmax assign a probability to each one. So the probability score is high, then that would be the most probable output of that input. So that's how we have this encoder and decoder blocks. So in nutshell, you can consider encoder as a expert or the editor who thoroughly reads and understands the original message. Okay, and this decoder is the generation expert who takes the summary from the encoder and creates the final output. And usually, like, it's a one word at a time. So the modern transformers uses encoder and decoder as in core architecture, and it's the same. We already talked about this feed forward network, like what it does is like it's a kind of like checker on the output generated or the information generated from this multi-head self-attention, and it resides in both decoder block and encoder block. So over here, like, it's showing the entire processing in work, which is taking input, creating embeddings, then doing this multi-head self-attention, and then parallelly, like, it's in a loop or batch, like it's doing this again and again the same thing, so that it can produce a contextual representation of it, which can be passed as an input to decoder, and decoder do this mass multi-head self-attention again, without generating any new thing, but review the whatever is being passed on by encoder and then do a forward feed FFN again, and then after normalization it produces the result as an output. So that is related to encoder and decoder stacks. And then we have this BERT, which is again one bidirectional encoder representation from transformers, is one of the most important breakthroughs in modern language AI language processing. You can think of a BERT as a highly effective digital language scholar trained to understand the full context of sentence by reading it. And over here in this diagram, you can see it's encoder only. There is no decoder because it's an expert to review and analyze the past information. So this language model was created by Google. As I said, like no decoder is there, only encoder model and contextual understanding of the text. So understand the difference of like the old NLPs and this BERT bidirectional encoder representation architecture. What it does, like earlier, the old NLPs, like the RNN we talked about, they used to read it from left to right only. This bidirectional means it actually can read from left to right, right to left, can understand the entire context of that sentence, the long paragraph or sentence, whatever is being passed. So it's very powerful to understand the basic context of this entire input which you are passing. So BERT is trained by taking huge amount of text and then randomly hiding 15% of it, then asking the model to guess the word. So if I say like a real-time example of BERT would be creating quiz. So next sentence prediction. If I say that it's a hot summer and if I go out, then I will feel very, then it will fill in the blanks with that particular contextual information thing. So it's not something like the BERT is not expert in generating outputs, but it's very much useful in pattern recognition, classification, and object detection kind of models. Then we have this comparison of all these three transformers, GPT and BERT. So in transformer, you can see like we have this encoder and decoder, which we already talked about in detail. And GPT is just a decoder only model and BERT is a encoder only model. So what it does is, like we talked about BERT, that it's expert in recognizing the patterns and then reviewing the things, fill in the blanks, object detection, all those stuff. And this GPT is expert in generating the content. So what was the role of decoder? Decoder used to generate the content based on the past input, and the past input which is fully processed by encoders and then being passed. But over here, for example, we want to write a poem on weather, let's say. Then this generative model, because it works in auto-regression fashion, it generates the stuff and then produce the output, refine it, then reproduce it. So that's how this GPT model works. Like these are expert in generating the creative content. So this architecture is perfectly suited for the continuous writing. So the key insight is, by simply training the decoder in GPT, stack on the massive task of predicting very next word in a gigantic corpus of text, the model is forced to learn grammar, context, and even reasoning styles. So now in next part, like we'll just take a look on Gen AI models and we will go through the few demos. And for demos, like I'll guide you, like as I suggested, that we'll be using the collab, the Google collab, where we would be using the Python code, and from there, like I'll guide you how we can do the Gen AI models and complete the code demos.